not sure how long this session is gonna be, but my idea for this one is gonna be I'll just put up a little thing here. So this is just gonna be like implementing yeah, so that's what I was gonna say. So basically I'm gonna go into the quad tree and optimize it a little bit, because I have an itch and I need to scratch it. So basically it's not really stemming from anything like having to optimize something, but it is, I know that the collision system is is one of the pain points, or bottlenecks I should say, in the simulation. And I saw one easy fix that I could do that might increase FPS for that. And maybe where we could see that more is maybe in the Linux version, because when I run this on Linux, I mean, I don't know how, there's probably some emulation going on. I'm not sure, because I'm running on WSL, so I don't actually know how that works, but I'm probably guessing that, I mean, it's a virtual computer, and then it has to, so yeah, so I don't know what's causing such slowdown on when I run on Linux. But also when you run on the WASM version, there's also like major slowdowns, or I mean, how do you say it? I think the largest time map that we have right now is like you can play on it, but it's like 20 FPS or something like that. Well, it depends a lot on maybe your computer and everything, but yeah, it's not good. So any tiny bit helps, I guess. But I mean, it is meant to be run, natively on your computer. So yeah, I don't think it's like a huge issue, but I just saw an easy upgrade that I can do. So I'm just gonna, optimizing quad tree. And the thing that I'm gonna check out is early, like basically when you're building the quad tree and there's only one entity left in sort of the pool of entities that need to go in to this region. Actually, it's I just realized that there's probably a bit of a problem there, but we'll figure it out. We could do something at the last entity, I guess. The last entity, yeah. I think the problem is because we're looping through each entity and adding it, right? And we're creating the quadrants along the way. I guess it's kind of hard to explain. Maybe, okay. But I know what the optimization needs to be. I guess like early early leaf. I don't know. I don't really know what to call this. Early leaf. So basically, let me bring up GIMP here to make it more clear. And I can use it. If someone joins here and wants an explanation, I can show this. Let's see. Hang on a second. Okay, so here's GIMP. Let's make a new image. All right. So, can you see the entire thing here? Yes. So, there we go. So, we have a quad tree here. Quad. I wish I had my pencil out, but I don't. I haven't fiddled with that in ages, so we'll have to live with this. So, image mode RGB. Thank you. So we'll have this. We have this boundary. So this is like the entire world of the physics system. So the idea is that there's probably no entity or very few entities that are gonna be outside of this region here. All right. So this is the first level. Actually, this is green, I believe, in the game. I'm pretty sure it's green, and then we have blue further in. All right, so let's imagine we have a couple of entities. So let's have an entity over here, and an entity maybe over here. Yeah, they are actually like rectangles, so yeah, whatever, it doesn't really matter that much. All right. Now the next step. So what we're doing in the algorithm, I'm pretty sure, like it's been a while since I've been there, but I'm pretty sure this is how we do it. Like we go through each entity and we're trying to find its place in the tree. And while we're doing that, we're looking first, okay, we start with the root node. Like, is it in the root node? Because if it's outside the root node or at the edge like this, we cannot place it in the root node. We have to place it like outside. And that's what's called an orphaned entity. But we're not concerned with that right now. So we're only concerned with the entities that are in the tree. Hello, Blue. How's it going? Welcome. I'm currently thinking about optimizing the quad tree. So so we're only concerned with entities that are in the boundary here. And so next step is to create the next layer or next quadrants. But we're actually only creating the ones that are like populated. So we only create this one and this one. But if we're going through this properly, because we're going through entity 1 and entity 2. So this is 1 and 2. So first we're going through this one. Maybe it's like hard to tell the difference here. I don't know. Maybe this one is like filled in. Okay. So we're going through the filled in first. Now these are blue. So we're seeing it. Okay, it collides with the green rectangle. Yes, very good. Next step is to put it in a quadrant. So we're looking for that. So we're creating a quadrant here. Now we have this quadrant. Now we place this quadrant in the green node. The green node now is parent to this blue one. And we can also write this like this. So first you have this, actually let's do just a line. First we have this is the root node. This is like level 0 or something. And then we have this as a child under it. So these are connected here, right? So this is the tree. This is the root node of the tree. And now we're in the blue square here, or rectangle, or whatever. And we can see that. And what we're doing, how did we find this? Well, we found it by looking for which rectangle of these 4 quadrants this collides with, and we found it's this one. So then we create this one, and now we go further down, and we do that until we reach a point where, well, I can show you, maybe it's a bit, let's actually move this guy up here to the center, because then that's the point where it stops actually. Next one is, I don't know, remember I think it's red. So next time we have these 4 quadrants here that we need to check against. This is a recursive operation, so now we're dealing with these the children of this, right? So we have these 4 children, and then we need to check which of these does this belong to. But we can clearly see here that it's not gonna it's gonna collide with everything, but it does, since it has like multiple collisions in this quadrant. That means it cannot fit into any one quadrant. So we have to go back and just place it as a child in this blue node. So this one will end up as a child to the blue node. Okay? All right. But the thing is, like, if the blue one was over here, let's say, well, let's put it like in the middle here, and we go back here, and now we create the red one again. So now we can see, well, I'm not gonna draw every quadrant here, but we're gonna test against everything. We can see that it's only colliding with this red one. So we put it in the red one. Now we create this red node. Okay. And the next step, I believe, is like yellow. Right? The same thing happens here. We can see that this intersects with every rectangle. So we can't place it in any one yellow. So we stop here. Now this child has the entity number 1 here. So what's happening here is we go as deep as we can and then place the entity there, right? But this is inefficient later when we need to check collisions against this entity, because we could just as well, since this is the only entity in this blue rectangle, we don't really need this red rectangle, right? We can just, if we have this situation, we can just put this up and like let's make a copy here, and we can remove this and move this up. Okay, so that is the optimization that I want to do, because this is the part where you can spend some time at building the tree, but then when you check collision, that's the part that's actually gonna take time later. So it's better to optimize this here to make it go faster later. So basically, I guess we could do a post, like we could still go through each entity like this and then place them here, and then in the aftermath, after we've done that, we check for which entities we could optimize like this. I'm not sure if that's faster, or if we could maybe change the way we iterate through the entities. So maybe we can go by, instead of going each entity, putting it in the deepest possible node, we could maybe go through each layer and check which entities are supposed to end up in each layer. Because at that point we know that there's like, if we divide the entities up in 4 every time, we know that, okay, this one didn't have any, so we don't create it. This one did not have any, so don't create it. This one had 1, and if it only has 1, or maybe we have like a, you know, a minimum amount, you can have a threshold, let's say 3 entities. If there's 3 or less entities, then we don't bother to go deeper beyond. We just create this quadrant and we're done. That could probably be a good optimization to do. I'm not sure if my idea came through here, but since I'm not explaining, I only explain this first one here. But I'm seeking, like, this is I'm showing the problem here and a possible, like, this is the problem with. Okay, let's do the full example here so it's not any misunderstanding. So next, now we're on. So one is done, and we'll forget about this one. This one is like. I'll remove that for now. So this is the scenario right now. Now we're done with one, right? So we'll go down. Now we're doing 2. Okay. So where is 2? So 2 is first. We're checking against. Is it in the root? Yes. Which quadrant is it in? So we're checking against all the quadrants, and we can see that it's down here. So then we create this quadrant, right? And then next step is to check the reds. So yeah, it's clearly in this red here. So we'll create this red one. It's barely in there. Okay, let's see. And then we also check the yellow. So actually it's in this yellow. So this will actually end up being quite deep down actually. So then we have a yellow. And you can see how inefficient it will be. Let's just stop there. Let's just have this. It will probably go one deep. Actually, let's do one more. I think the next one is like orange. And let's just do this so we can see. And then now it stops because it won't go down deeper there. Okay. And now this one is number 2. So you can see here when we are going. And why is this inefficient? Well, it's because when we want to check for collisions. So let's say this entity want to check collision against this entity. Well, we have this rectangle, and we want to check where it collides. So the algorithm goes like, first you check against the root tree, and it collides against the root tree, right? Because it's intersecting the root tree. This rectangle intersects with the root tree. Yes. Okay, then you check which of the quadrants does it intersect with. So checking not here, not here, not here, but it is intersecting here. Okay, so then we go deeper again to the red ones. It's intersecting here, 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 here. So we're intersecting here, right? And then we can't go any deeper, so we have to stop there. And also along the way, we're also checking like if we have any entity children along the way, which we didn't have now. Well, except for this one, but that's the same one. So we skip that one. So there was no entity, there was no find there. However, if we want to check this one, so also if you noticed, we went through the entire tree to go down here, right? Or the entire branch here. Okay, but this one we have to first check the green one. Yes, it collides. Then we check all the blue ones. So that's 4 checks. I don't remember if I had like optimization for there, like best order prediction or something like that. But basically 4 checks. Let's say we're going down here. Okay, 4 checks more, 4 more checks, and we're going into here. So that's what, 9 checks, then 4 more checks, and we're going to here, and then 4 more checks, we're going to here, and then we're done, right? So that's like each time we go down the tree, we have to go do like 4 checks. But you can clearly see that we don't really need all of these subdivisions we can simply move this up to the blue one. So basically, in more optimized a more optimized version is going to be basically this now, which really does the same thing because there's only one child in each branch, and this is also if we have and if I reflect this over here as well, whoops. So this is the more optimized version here, which does the same job, and it divides them. And this is also like this is also like if you have a minimum of one entity in each, or a maximum of one entity in each. Yeah, if the limit is one entity in each cell or subdivision here, or quadrant, then this is like the most optimal way of doing it here. But this is the tree that we generate now, and this is kind of the optimization. But you can also say that, okay, well, what if we allow 2 or 3 or more entities in one quadrant and then call it a day? So basically, if we say that n, let's say n is the number of entities in each quadrant, or the maximum allowed, I guess, entities in each quadrant. Let's say that this is 2. Blue, yes, it is for checking collision, yes. And the reason why it's important is because, well, for one, you want collision detection, but the reason why it's like well, an important issue to optimize is because collision detection is one of the most resource heavy things you can do. Well, in my game at least, it's the definitive like bottleneck in the game, because there's so much calculation you have to do depending on how many entities you have. Okay, so if n is 2, that means we allow maximum of 2 entities in each quadrant. Well, then we just stop at the root node because we have 2 entities, so we should just stop here. So now the tree looks like this, and we have basically the same number of checks. So 1 and 2, and we have the same number of checks because 1 needs to check against root, that's 1, and then all the quadrants, that's 4, so that's 5. Actually, this is more optimal. 5 checks, and then we're done. This one, you only have to check 1, because there are, well, actually technically we only have 2 quadrants, so that's not entirely true. You don't need to check against all the quadrants, you just need to check it against the quadrants that exist, because I do have like optional quadrants, so the quadrants that do not exist we don't need to check. So this is like, if you want to check which this one entity collides with, you have to check against root, well, it doesn't matter if you check against root or not. Everyone checks against root, so we can just remove that check. But basically, you check against this quadrant and this quadrant. Because you need to check if you have entities that are, like, you could have an entity up here, for example. Then you need to check all the entities in each layer as well that you go down. I mean, okay, technically we could start at the bottom level and then go up instead, because then you only go one path up. Let's say you have like another one here. Now we don't need to, and then a one here. If you check with one, if you start at the top, you check against 4. You go down, you check against these, but really you don't need to check these because we're already a member down here as well. So that might also be actually a way to optimize. Yeah. So there's like, I thought that my solution was, I mean, I didn't think it was perfect, of course, but I didn't think it had that many ways to, I mean, I guess I never investigated thoroughly how to improve it. It was mainly, the problem mainly was in the beginning to actually build it so that it actually worked. Yeah, so there are some optimization we can do. And I think in order to reach this result, I think we probably want to have an algorithm that instead of looping through each entity and putting it in the deepest possible subdivision, we will go through each layer and then keep track of which entities are getting orphaned and which entities are divided into each quadrant. And then you do a recursive operation on each quadrant. And the orphaned ones are gonna end up in, like this is an orphaned, let's say. You have an orphaned. Well, this is not, technically this is not orphaned, because you can have, if you have an entity in the middle, this is sort of this is not orphaned actually. Well, orphaned is a bad word. Orphaned means that you're out here. So orphaned is by, like, you're not part of any quadrant here. But if you're in the middle of the entire thing, then you're in the root node because you're colliding with every possible quadrant of this root node. So then you end up here. So this is 4. Oops. 4, 1, 2, and we don't really have 3, but let's say 3, and 3 is like outside. 3 is like up here. I'll make this into 5 maybe. So maybe 5 is over here or something. Well, you want to check if player is colliding with something or not, right? Just check nearby objects to the player. I mean, yeah, that's the whole point. Like, that's the whole issue. Like, how do you do that? It's just like, it's just like anything with programming. Like, you ask the question, okay, how do I do this? I know what I want to do, so how do I do it? Right? And I mean, there's a super easy, naive way of doing it, and that is going through each object and checking for like rectangle collision against every other object in the scene. But that's called a brute force algorithm, and that is like very, very slow. When you get more entities, that will slow the computer to a crawl. So so this is a way to make this algorithm like checking, like this is a way to eliminate a whole bunch of checks. I mean, check which quadrant the player is only. Yeah, yeah, that was what I was talking about. Well, I talked about a lot of things here, so I don't blame you here. But I did say here that, let's say number 1 is the player, let's say. And we want to check which collides with the player. So then you can start down here at this blue quadrant, and then you also have to go further down. Oops. You have to go further down if there's any children, because there might be collisions down here. But if you go, then when you go up, you only need to check this blue quadrant. You don't need to check these ones, because we know that 1 is in this quadrant. So we don't need to check these quadrants. but we do need to go up and check if there are any loose entities or any entities that belong in each layer. We do need to check those. No, don't be sorry. There's no problem. I totally understand how you could miss it, and I might not have explained it clearly. And but yeah, that is a good point. That is a very good observation. And so basically, I think there are two optimizations that we could do to the quad tree current implementation, and that is to optimize the tree so that we don't want this 3 here, so that a structure like this basically can't happen, and instead we want a structure like this to be the result in this case, right? The second part is to double check how we're doing the search when we actually check for collisions. So this part is about building the tree here, and this part is about like searching the tree. No, there's no issue. Everyone can, you know, miss stuff there. That's no problem. So anyway, let's, I guess we can go into the code and see how it looks. Okay, so actually this is like, let's optimize building the tree. So we're basically removing unnecessary layers, I guess. Either we remove them afterwards, or I think it's better. So the better path is to the algorithm that I proposed there, like going through each layer, and instead. So layer wise building of the tree. I don't know if that's clear what the hell that means. And then optimize the search. So this is like bottom up search. I would call this, I guess. It's not really bottom up because you're starting at the node where the entity is, but that is that's the thing that we want to do. Hello, Vicent Lenkar. How's it going? Sorry if I botched your name there. Are we doing SimD? Well, Zig has like built-in vectorization if you're using vectors, like the built-in vector type. And for quad tree, I don't think I'm using any of that. If we split by 8 instead of 2, we have a 64 AD tree. Well, I'm not splitting. Well, let's go back to the drawing here. I'm not sure. I am splitting by 4. Okay, it's not clear here. But it's a quad tree, so it is splitting like by 4. It's just that I tried to draw this before and I had it like this. So basically we have these quadrants here, and this over here, and this over here, and this over here. Well, this is like the unoptimized version. And what I was talking about earlier was that, and I mean, this goes even deeper here, actually. So this one also, the 2, it goes like this, and then even further. It's kind of hard, but to see, but it goes like this basically. So the way the algorithm works right now is that I go through each entity and I put it in the deepest possible subdivision. And this probably goes even further as well, which is a pretty, you know, this might even go one more, but pretty unoptimized way of doing it. I mean, it's not horrible, I guess, but it's I can see a way to optimize basically this structure here. So what you said about splitting by 2, like it's 2 here just because we only have 2 entities and they belong to a different thing, but it could split up to 4 here. So it's a quad tree. And the optimization that I want to do is turn this into this. Or, I mean, not turning it into this, but basically the result is this now. And I want to have this as the result, basically. What if object lies between exactly 2 only? Yes, good question. So, example 4 here is, you can see it's clearly in the middle of all these. Well, it's in the middle of the green one. So it intersects between all these 4 blue quadrants. So we put it at the top layer. So we put it at, so basically each layer, like the green is one layer, blue is the next layer, and red is the next layer down. So green, we put it in the list of children, like entity children for green. So you can put it directly under green. So each node, each layer here has a list of entities and also a list of like children, like quadrants here. And there's also another category, which is like if an object is outside of the whole thing, then it's building the tree and prevent this from happening. Like you get these super deep branches unnecessarily, and I want to have this as a result. Did that clear things up, Vicent? I'm gonna call you Vicent, if I may. And we have collisions over here. I am, however, using SimD when updating the positions and stuff like that. Positions, velocity, and gravity calculation is also done with SimD. But it is using like the built-in vectorization from Sig. So I'm kind of relying on that to work, but yeah. Yes, you can see I have like a bunch of different collision algorithms, but this is the one that's active, so it's gonna be happening in here. And basically, well, this is not where we build the tree. Where do we build the tree? I think. Wait. No, that's the positions and stuff. Is it in here? Maybe it is here then that we build the tree, maybe. Or do we do it somewhere else, perhaps? Hang on. Let's see. How do you know the granularity if you go bottom up? Could you explain what you mean by granularity? So I can explain like how I'm thinking the algorithm should work. Is that okay? Now this is not really how it looks, but let's look at this tree here. Okay, so let's say we have another layer. Okay, let's go through how this works first, basically. So let's say that, okay, which one does 1 collide with? Okay, so what my proposal is that the bottom up is basically we start at this layer because that's the layer that this belongs to, and we're checking then if there are any other entities in this layer, but which it could be like we could have another entity here which is 6, and then we check against that one, right? Yeah, so the size of square, so that would be wherever it quadrant it belongs to. So basically each entity only belongs to 1 quadrant at a time. So there's a 1-to-1 relationship between, you know, 1 entity and 1 quadrant. I mean, there's here's like a 1-to-many between quadrants and entities, but yeah, it's a 1-to-many, but each entity can only belong to 1 quadrant, so we know which quadrant it is at that point. We just need a way to find the quadrant, basically. But we could use, I don't know, if we already can, use like pointers or something to get there. Going top down split until there are 2, then you find a smaller quad to check. Yeah. Are you talking about building the tree or searching in the tree? Because this is the bottom. Oops. This one. This is about searching the tree. Like you're already built the tree. But if you go bottom up, what's the size of your first quad size? I don't know if you're confusing that with the building of the tree. Like now I'm talking about searching the tree. Like you already have the tree built, and now we need to know, okay, which entities is 1 colliding with. We're not building the tree in that sense. We're not building the tree bottom up. We're building the tree. The tree is built from top down. Yeah. And I mean, and the boundary is also interesting because the boundary with the top level is determined by how large this the scene is. So the scene has a boundary, and that's the boundary of the physics of the quad tree. But then you can have entities that get outside of this boundary, but they are then like orphaned. Yeah, no problem. I was thinking like, well, there was something, some information missing there. Okay, well, let's see. So let's like there was ages ago since I was in here. This is basically the first thing that I implemented, basically almost in Zig. So which was like a year ago or something like that. Man, time flies. And I mean, I've been in here from time to time, but okay. So here we have like populate and intersect. So right, quad tree. Oh yeah, I'm in the wrong thing. Quad tree. Oh, okay. Yeah, so here's that populate and intersect. So this function is the main. This function builds the tree. Yeah, we're rebuilding each frame. We're rebuilding the entire thing. So we're resetting. That basically just deallocates everything and resets everything. We get a bunch of entities here. So these are entities, like entity IDs here. And we also get a... I think this is a function or context. Yeah, don't remember. I think this might be the registry, maybe. I don't actually remember. Let's check. This is called. Which one is it? The after entries. Okay, it's the container. And then we have intersection handler. Okay. Yeah, so each end, so we're checking, like we're populating a tree, and we're also at the same time checking the intersection. So this is why this is kind of, you know, we're doing everything at once here. I didn't answer your previous question. Oh, sorry. Let's see. Was the question, what if an object lies between two quadrants? Well, I thought I answered. I mean, so I said that this. Well, I don't mean to. Sorry, I don't mean to say like I already said it, but okay, this is colliding. Right, the 4 here is colliding with all of the blue ones, right? And what happens then is that it gets put in the parent of these blue ones, the green one. It's the parent, like this. So it's just put. It can't. Since we can't put it in any one quadrant of this list of quadrants, we have to put it in the parent. What if 2? It's the same thing. Like, because if we have it over here, let's say 6 is over here, this also cannot be put in any one quadrant of these 4 quadrants. So it has to be in the parent, because we can't determine, like we don't divide these 2 into a separate rectangle and then keep children there. We just put it in the parent because it can't fit. So we'll put only, yeah, so if it intersects any of these lines, and all of these will end up as children of the green one. So all of these will be children over here on the green one, which is very inefficient because then these are gonna be checked against basically everything. So it's also like I guess the weakness of the quad tree is when you have things that are like in these middle lines here, because they will not be super optimized. Yeah, no problem. And the same if you have a thing here. This will also get orphaned, which means it's put outside in a list here. And all of the things that are orphaned, they have to be brute force checked against everything else, because they're not part of the optimization tree here. All right. Okay, so I lost my little thing here. Let's see. Whoops. Okay. Whoops. And this was build. What the hell was this? Building. Man, I forgot what I said. Bit like optimizing. I want to say like pruning, but we're not really. Pruning is more actually you do afterwards. It's more like collapsing, I guess. Yeah, collapsing. Well, that's also whatever. I'm gonna call it like collapsing branches. And then bottom up search. There we go. All right. I mean, I don't mind asking you asking questions. I like explaining, and hopefully teaching something would be cool. Okay. So we got this function here, populate and intersect, and well, as I said, like it does like both things at the same time. It does both the building of the tree and searching the tree, and basically all the entries that's put in here, it's gonna check all the entries because we need the result for collision detection, but then also the tree is available later when you want to do, you know, you want to check a rectangle that's not an entity. You might check, okay, let's do an ability that targets this area. So there you want to know which entities are in this area. Then it's very good to use the tree to search for things that are in this area. And also like for attacks to check collision against like an attack area or something. So we keep the tree around, but at this first point we also check like intersections between each entity, which might not be, you know, sometimes we don't care if something intersects, like if they're basically, if they're not colliding, well, if they're colliding but they're not solid and they don't like affect each other's physics, then it might not be of interest to check that. But we still, you know, you still need to check. I mean, we still call this function for each entity that gets I mean, we still need to check every entity unless the entity is not part of any like collision group. That's also a concept that basically defines which entities block other entities. So ground blocks player, for example, but the player doesn't block a monster, but a ground blocks monster, and so forth. But that's not part of this system here. We're only interested in optimizing the actual building of the tree and searching the tree here. So let's look at this. So what are we doing here? We're setting up some stuff. We're calculating how many pages are needed. Interesting. Pages needed. Because I think page is the concept of layer, as I was speaking. Like the green is the first page, then the blue ones are the next page. I'm pretty sure, although it is recursive, so sorry. I'm a bit tired. Pages needed. Yeah, I need to deep dive into this again too. But this is basically, yeah, this is why it's gonna take the entire stream here, is because I need to go in here, check what my past self coded up as like the first thing in SIG, and learn it all over again and find maybe that we couldn't do it or something. I don't know. We'll see. Okay, well, okay, so pages needed. So I wish I added some more explanation here. This is where documentation would be really good, when you have like things that are so complicated and you have this. I wouldn't expect this function to exist. Like, I mean, I understand maybe we want to allocate based on what's needed, but how can we calculate how many pages are needed? I guess this is like the maximum, maybe. So we're looking at how many entries there are. Oh, so we do have max entries in page is 10. Wait, we already have this number? Okay. Well, I guess it makes sense. But when you play the game, it shows. Let's see if we can make this work here. No. Corrupt header. Let's try this again. Okay. I don't see it. Okay, there we go. I enabled, this is like the collision. It's a little bit weird since things are going like into each other here. You can see the FPS. Well, this kind of is calculated from the FPS. So if you have more okay, the circles are not activated, I guess. But if I activate the quad tree, you can see here that we are going like this entity up here should it's really inefficient to have this quadrant and this quadrant and this black one. Like, it should just be this, or even this, because there's only one entity here, so there's no point in dividing it further. You're not optimizing, then you're de-optimizing. So that's the kind of the problem here. Okay, I just wanted to see if we could run this and see what's going on. Actually, did you see it? I didn't see if you actually saw this. Oh, you didn't see it. Okay. Great. 1 second here. Can you see this? Okay, here we go. Now you see. So basically, yeah, if you see this this square over here, it's what I'm controlling here in this demo. So basically here, now we have this quadrant, the purple one, or magenta, and then the orange, and a tiny black one. Is hard to see here. But the orange one, the pink one kind of makes sense, but the orange and the black one is just that just adds more checks to be done, because you need to go deeper into the tree to reach this entity here. So that's what I want to avoid. So basically, this should not be black and orange. This should be only magenta here, like this. This is the result that I want. Whenever this thing is in here, because there's only one entity, so there's no need to subdivide it further, right? So so that's good. We can test that and see if things still work when we edit stuff. All right. So, but that's what I was curious. Like, how do we know how many pages are needed? If, like, do we know how deep we're going if we don't consider any of the sizes or anything? So I'm not sure. Maybe this is like a guess to avoid multiple allocations or something. This really depends on the size of the body. Yeah, so this is exactly what I was saying. Like, it depends on the size of the... Like, if you have 1 by 1 pixel body, it's going to be sort of almost infinitely... Not really infinite, but it's going to subdivide so long down. Like, we're not going to have, like, a 1 by 1 body, but... Yeah. So, basically, this is just guessing, and then we kind of wing it, I guess. But it has to be adjusted later if we need to, right? Prepare to add pages. Right, so resizing page. So I think this is just or do we like add page prepared? No, this just sets it straight off here. Okay. But this might be called like multiple times. No. Is there an add page not prepared? Nope. Okay. Well, that's concerning, but whatever. We're basically guessing how... Okay, well actually, now when we optimize, it's gonna be less of a concern actually. Because we're gonna collapse the tree anyway to remove amount of pages. So, okay, let's go through this more here, because I need to refresh my memory. Right, so we're adding a page. So what does that do? So we're just setting this to a page. So the page is basically each layer. So the first one is the green layer, that's the boundary, that's the whole thing. And then we have also a list of entries. So this is basically a node, you could say almost. Yeah, we also have a position. Why is this an index? Offset. What? Okay, now I'm confused again. Max entries. Oh, right. So we do have like a global list of entries. Oh yeah. So this is how we can see which entries are in which page, I guess now. So, but we also have quadrants, right? There should be quadrants in here. Yes, they're quadrants, but they are all start out as null. Okay. Oh yeah, I was playing around with the generics here. Subdivision page. Subdivision is just a struct with top light, top red. So basically this concept got reused over and over again. So I decided to make a generic subdivision that did that. So that was nice. And here's just a subdivision of page or optional page pointer. Yeah, there was a bunch of convenience functions here. Okay. So, right, so we make a new page. And we have a pointer. Right, pages. So pages items, that's where the pages are stored. Why do we have like a page index? Well, okay, I guess it's because pages. Okay, I'm so used to using just array lists that it feels strange to do this. But because we probably don't really need to do this. We could just use an array list. I mean, I guess it's more optimized. Maybe. Wait, this is an array list. What the hell? Why do we need the index? Okay, I'm not gonna question it right now. Current entries index. Right, so yeah, okay. So we're like pre-allocating the number of entries. Yeah, we have this one, entries. Resize 0. Where do we set it? Oh, that's what gets populated. I see. Okay. Yes. Okay. So we have this self entries list that basically the first 10 entries of this list is the first page. Next one is like the quadrants of that. So everything like the entries and the pages, these are both like pre-populated, or not populated, but pre-allocated for all the possible pages that we could need for the tree. Okay, so we're using a bit of memory there. Then okay, so that's what this was doing here. So yeah, we're just bumping this up. Okay, fine. Okay, then this is what I was talking about. Then we're going through each entry. Now this is what I want to change. Like, instead of going through each entry and then finding the deepest, because that's what we're doing. We're finding the deepest quadrant or subdivision to put it into until it can't, you know, it can't divide any further because it's like intersecting multiple quadrants. And that's what I want to change. So instead of going through each entry, I want to go through each layer instead. So so how I'm gonna do this is I'm gonna copy this and call this something else. So this will be like a new test here, intersect, and this will be like layer by layer or something like that. Okay, still the input should be the same, but instead of going through all entries, we're gonna go through all the pages. So where are these guys? I guess we have like pages. What is going on? I mean, I haven't. Okay. I'll just ignore that. Let's see. Whatever. All right. So how would we do this? So I think we go through each page and we could probably do like pages items. Actually, okay, so no, we're doing this now. The only concern here is that it's not really recursive now because we're going through each page. We just start at the root page and then recursively go down. We don't loop through. We don't loop through like this. So we should have another function that is build layer by layer or something. I don't know what we call it. And we pass in the root node, which should be the first page, I'm pretty sure. Maybe, yeah, this. No, that doesn't need to be a pointer, right? Maybe? No. Maybe? No. Well, let's make it a pointer anyway. Okay. So this would be build layer by layer, and we're gonna actually let's do self. So quad tree, and we have the page, which is a page, and void. Okay, so that's gonna be it. I need to BRB 1 second here. Sorry. All right, back. Okay, so okay, yes, building layer by layer, yes, brick by brick, layer by layer. Thank you, Blue. Yes, so how do we want to do this? Well, I have to look at how we actually do it. I'm almost tempted to like no, I'm not gonna redo this whole thing. That would be an endeavor. I mean, I might do it actually later because it's like since it was one of the first things that I did. There's maybe, if I did it again, I might do it in a different way. But then again, maybe not. You know, there's... I did put a lot of effort into this. And it's not totally stupid. So, but anyway, it's just, it just feels like there's a lot of inconvenient things here that I need to learn and get myself into here. So yes, brick by brick. Okay, now let's see the other one. It goes through each entity. We are getting the entry. So basically we do want to sort of do this, except we only want to do it for the current layer. So actually I'm gonna copy this part, put it here. Now the entries that we are concerned with also we need to sort of keep track of here. So we could have, so we should have like the entry. Now I'm not sure if this is possible. Because the entries are... Nah, it should be possible. Now this is a list of, I think this. Yeah. But now this is like a sub list. Because each time we're going through each layer, it's going to, we're going to recursively call this function, and this is going to be reduced, or I mean it's the next time we call it, we're going to call it with a different with a filtered list, I guess. So I think what we want to do is we want to have a subdivision for entries, quadrant entries, or subdivided entries. So this will be a subdivision of excuse me, of these guys. Okay, and it starts with undefined. Okay. We can start with empty lists. Okay. And then the idea is that when we go through each entry, we just check. There's like, I guess 3 scenarios. Like the first one, if we're in one of the quadrants only, then we put it in one in the corresponding subdivision here. Actually, let's make this into an array list. And now these are empty. However, we could initialize them with capacity, I think. Yes. But then we need allocator. Do we have allocator here? No. We can't pass it here though. Allocator. Alright. So this would be capacity with allocator. How much capacity? Well, it's gonna be like max. No, it's not gonna be max entries in page. It's gonna be like entries length. It's never gonna be more, but it's gonna be able to be up to entries length, I guess. Okay, now this might be kind of inefficient. Like we probably want to do, instead of doing this, we probably want to do like one allocation for all 4 lists, and then have each one be like like a slice. Yeah, let's do that instead. So I'm just I'm prematurely optimizing here. So basically, quadrant. So actually, subdivided entities buffer. Or list. I'll call it entries, I guess. Array list of k init capacity entries length, because then we don't actually need 4 of them. Whoops. Okay, there we go. And then this would be this would actually be just a slice. And we'll start with empty slice. But they are all gonna be put like sliced into this list here. The problem is now, where do we put this list actually? And no, this should just be like temporary. In the end, we're gonna put stuff in the page. Yeah, this was a bit more tricky. Like, it's tricky when you're optimizing also like memory and stuff like that. Well, I guess it's not really memory. I guess it's like how many times we need to allocate, where do we put things. I'm not sure. Well, let's just keep going and see how far we get here. Maybe I should have focused on trying to do this here, but we do need to solve these problems. Like, where do we put the thing? Okay, I'm not gonna worry about that for now. So what we need down here now is we need to check if we're intersecting with the quadrants. If we are not, so if we're intersecting with more than one quadrant, it should end up in the page entries. If it intersects only one quadrant, we put it in the corresponding quadrant here. If it otherwise, it's an orphan, basically. So that we put it into orphan. Now we shouldn't get orphan entries once we've moved past the root node. We should only get it at the root node. Because then all of the entries should be part of the tree, of the boundary, inside the boundary of each quadrant there. Right, so here we're going through all the entries. We are getting some sort of value. Not sure. Oh, this is the actual like key. Okay. Okay. Wait. Oh, this is the index, and this is the okay. This is kind of weird how I named this entry. Wait, yeah, because this is like the index. And not the entry. This is the entry. Okay. Right, now it makes more sense. We're going through each entry. We need the index because we're using it here. For some reason we're inserting. Right, I think the insert is the magic part here where we're actually inserting the entity into the tree. Yeah, so that's how it worked before. Like we yeah, but now like each, like you could see it like this. Like before, each entity is treated like an isolated entity that gets inserted. So the whole operation of inserting an entity or building a tree is isolated per entity, you could say. But now I want them to all coexist instead. So we can optimize. So we know that, okay, we only have one entity left here, so we don't need to go any deeper. We can bail out, and that will give us less branches, or yeah, less pages. So let's check here. So we have orphaned. So basically, I think we want to do, we want to change this operation to, instead of inserting into the tree fully, we want to oh, also we're doing intersections. Okay, this is interesting because this could turn this whole thing on its head, actually. Because this is, okay, this is interesting. I didn't remember this. Well, think about this, actually. So every time we insert a new entity, we also check for intersections. I think what this does is it prevents like double checks. Like if you're inserting the first one, then there's nothing to check against, so it's fine. You insert the second one, now you have one other to check against, so you do a check. But you only do a check against the first one, and then you insert a third one, you do a check against the first two one. But crucially now, the second one didn't check against the third one, but the third one checked against the second one. So there's no double checking. So that is actually interesting. So how would we then transfer that concept to the new way? Maybe if we say that, okay, we wait until we're at the we know that we should bail, like this is the last page, now we go through each one and check. Maybe. But then you might have like, you might have a tree that is not fully formed yet. I mean, yeah, because before that it didn't matter that the tree was not fully formed. It was actually good because it reduced the amount of checks, I think. But now you can have a bunch of entities, like you can have 100 entities in one quadrant and it has to check against each one because it's not like completed yet there. I mean, I think the one maybe option would be to figure out a way to do it after, like instead of intersecting while we're building it, which does make sense in the old way. We can do intersections after we built the tree instead and figure out a way to prevent double checks. I'm not sure if that's possible though, in a good way. This turned everything upside down. This turned everything on its head here. I mean, we probably still want to try and optimize. Maybe the problem is that, like, I thought first that if we still did it entry by entry instead of layer by layer, you could say that, okay, let's say we do entry by entry, but then we bail out whenever we say that, okay, we only have one entry, so we don't need to subdivide. Now instead you have like a dynamic tree, because if you insert another entity, you have to reposition the first entity that you added, potentially. Now you have to divide into several quadrants, potentially. And you have to also check now every entity along the way. If needed. Okay, maybe this was a... Maybe, well... Okay, maybe the collapsing branches is hard to do though. But the bottom-up search should be possible, I'm pretty sure. Yeah, this was well, at least we refreshed our memory a little bit. If it weren't for this, we would get a much more optimized tree. But if we had a dynamic tree, that would be even better though. Like an optimized dynamic tree. But that's super difficult. Yeah, I would have to rethink the entire algorithm here. Okay, let's scrap it. Actually, let's scrap this optimization. I will keep it in mind, but it's probably not gonna work here. I mean, we could. The question is then: is it better to have double checks, or is it better to skip, or is it better to collapse the branches? Like, it's kind of like we're choosing between two things here. And since we already implemented, now I'm gonna bail out here. I'm gonna cut my losses. Okay. Go back to 0 here. Oh, this is actually new. Oh yeah, this is intersecting line. That's right. Okay, well, I'm just gonna undo everything, so I'm sure that it's back to where it was. Okay. Okay, well, okay, so collapsing branches failed. Let's do bottom-up search. Okay. Yeah, so this would be this one. Here is the function for checking, for searching. So we have a rectangle and a chord tree, and we're gonna produce a list of intersections. And here, let's see what's happening. So we start at the root. Yes. So that means we're doing a top down right now. So that could be improved in theory, maybe. All right. So we're checking for orphans, and that we need to do anyway, so that's not an issue. But this is the issue. So instead of starting at the root, we want to start at the quadrant that the entity is in, and then go upwards through the tree to skip checking a bunch of quadrants. It basically means that for each page we want to skip maybe up to 3 checks. Yeah. Which could be significant. Let's check this one. So we're checking if the page is intersecting. That's fine. Okay, if it's not intersecting, we're done. Then we're going through all the entries and intersections. So this is like a top-down approach, right? So I think what we want to do is we want to rename this to top-down, because we need both algorithms. I want to have a separate one for bottom-up as well. Okay. And we really don't need to check for intersections on the, No, we know that we are in this one, so we don't need to check that, because we basically start at where we are and then go up. So now the only issue is, can we get the parent? I don't think, yeah, we don't have the parent, I don't think. Oops. How do I do? Oh, this one. Parent. No, there's no concept as parent, but we can add it. we can add the parent. This is nullable because it could be the root. And this, I guess this could be an index. It could also be a pointer. I'm not sure. Actually, a pointer might be even more efficient. Let's do a pointer. That should be fine. Now where is that add page thing? Okay, add page boundary. We also need a parent. So this one is the root. Parent. So that one should have null. Now then we're in here. That should be the page. Okay. So now we have a parent. Hopefully. Right. So now we can go through that. So, but we do have to check if we have a parent. Okay, but let's do the entries first. So we're doing that. That should be the same. This shouldn't be any different. This is just creating an intersection if there is an entry intersecting. We're not looking at the quadrants. We're checking. Yeah, we're never looking at the quadrants actually. We're checking if we have a parent. Then we also do intersecting bottom up. Yeah, I think it's actually pretty simple. And this would be the parent. Yeah. I think that's it, actually. Yeah, we don't need to look at the quadrants because we just need to look at the parent, the parent, the parent. Yeah. Okay, cool. So that's way more efficient. That's where we save the computation there. Oh, this is called in multiple places. Oh, the quadrants, right. So the way we want to change this, I think I want to copy this just to make sure. Let's do bottom up. All right, now the problem is, how do we find the quadrant? How do we find the page that is for this entity? And there's no entry going in here. We only get an A and B. But I'm pretty sure that we have the entry. Yes, we do. Actually, I want to make this change here because it was a bit confusing here. Okay, so we have the entry. We should pass that. We also have the index. Maybe we can use that. I don't know if I have a good way of getting which entry belongs to which page, but that would be a good thing to have. I mean, we could probably just add a list. A list that corresponds, like a map from entry indices to page index. Maybe. Because I mean, we could loop through the pages and check, but that's seems very unoptimized. So I think we will make a list. Let's do it here. So let's have like entries to pages, and this would just be, well, it could be an array list, I guess. Yeah, let's make it an array list just to make it convenient to use. So the index in this one is the same index as in entries and entry values. Those are the same. And then it maps to an index in pages. So this should just be a usize. I mean, I guess technically it could be, I mean, it could just be a pointer to a page, actually. Actually, this should be nullable because we could be, or it could be an orphaned entry. Yeah. Okay, now we need to populate this. So where do we do that? So we do that when we build the thing, which we do over here. And at the end of this here, so here we should actually do orphaned entries. No, not orphaned entries. Entries to pages. And this is gonna be null. And then otherwise, if we did succeed to add it, wait, how do we know which page it was added in? We don't have that. Oh man. Okay, so I think, yeah, we actually return a nullable page there instead. And let's assume we have it. If we actually have it, we get the page there. There we go. And set this to the page. Alright. Hello Polaris, how's it going? Not today. I'm doing optimization of the quad tree code. Okay, so now we got this insert returns a optional pointer to a page, so we need to change this as well. The Dad Walking, hello, welcome. First time here, yeah? How's it going? How's Gamedev with Sig? Well, I will preface to say that I'm not a seasoned game dev. This is basically one of my first, I guess, endeavors into game development. But, you know, I've tried different tools and stuff, but I just feel like Zig is nice because it. I can't really compare it to like C++, but because I haven't tried, you know, making a game in only C++. I have done a little bit with Unreal Engine, but only like blueprints. But I have C++ experience from way back, but I would say that Zig is very interesting programming language, and I really enjoy working with it. So from the perspective of a programmer that has like learned a couple of different programming languages and have about 10 years in professional web development experience, but I also self-taught in C++ before that, and I was interested in game development, but I never got around to actually do anything basically. But yeah, I really like Zig. It's a breath of fresh air, I would say, and some of the features are super nice to like convenient, and I really just love the low-level programming as well. Like manual memory management, sure, it can be a pain in the ass sometimes, but at least you feel like you have total control. You found SDL pretty cool to work with. So SDL, right? I actually used SDL, I think the first version, like a very long time ago. I mean, it's kind of like those libraries like SDL. I also used a library called Allegro that I think was like more maybe for like DOS and but it did work with like early, like it did work with like Windows as well, but yeah, it was a bit of a pain to set up in those days as well. But basically, I was gonna say like all those libraries feel like they have sort of the same features, but they are a bit different. I guess some of them might have like more advanced features and stuff, but I'm using Raylib here, so it's yet another of those libraries. But I feel like it's very simple to use, very like fast to get started with, very easy API. You don't have to do a million things to get started. So I think it's really nice, especially in Zig. Okay, so this one now should return that. This one should return null. Alright, let's change you. Optional page pointer. Whoops. Okay, return. Okay, so true. It says true, which is false. So we return null. Okay, actually, I mean, we could do something like this, but I feel like this is going to be very badly formatted. So return and then this. And if that's null, we can do or else this. Yeah, and if that's null, then the result is just null. Yeah, the formatting didn't work here. But I'm not sure how you would do that actually. Can you do this? Or this? Okay, this, you can do that. Okay, I don't like the formatting here, but whatever. Okay, now I need to change these ones as well. But I really like this. This is a perfect example of a really nice refactoring. Like changing a bool into an optional is so nice in Zig. It's just yeah, it just fits so well with all the patterns and stuff. Okay, return false. So whenever we return false, we should return null instead. Here we should just return. We should wait. This already returns this. Oh, that was the same function. Okay. Okay, cool. And then we have this one is this. And if that, we return null. Otherwise, now we can return page. Finally. Okay. Cool. No errors. Interesting. It's the calm before the storm. Okay. Yes. Great. And yeah, so now we get the page. So if we get a page, that means we got a page that we inserted in, so we can set the entry, the mapping here to that page. So now we know now we can just, if we have an index to the entry. Wait, but we don't have. No, wait, we should. Yeah, we should have it. Yeah. Otherwise, it's an orphan entry, and then we just put null there. All right. Now, here we can say which entry we're talking about. So we need the I. And I'm gonna call you entry because it's confusing. And then wait, this is the wrong. Yeah, I want this one. This is gonna be the entry. Yeah, you don't want the entry. I want you to be bottom up. No. So we're changing out the algorithm here to bottom up. And why am I asserting the root is not null? That's a weird assert. Let's remove this. I think this is optimized away. Whatever. Let's keep this here. It's also, you know, whenever I test this code, I actually never run the actual optimized version. I don't think it's always like the debug version. I'm pretty sure it's the debug version because it takes it just doesn't take long to, or it takes longer to compile the optimized version. But anyway, it's no big deal. Let's see. Yes, so here this is interesting. So yes, we should check orphan. That we need to do that anyway. But this one, so we want to check bottom up now instead. But the problem is, yeah, we need we don't. Actually, you know what? Let's remove this because we need a page. And what is the page? The page is entries to pages, items, entry. That's the page. Actually, we could assert that that's not null, I guess. Page is not null. Okay. Right. So we have the page where the entry exists in, and we're going bottom up, which means we're checking all the quadrants, like all the pages upwards, but we also need to check the children. So we actually need to check the quadrants as well of this page. So we're checking the bottom up, which does check the entries in the current page, so we don't need to do that again. And then it goes up the parent there. And then we're checking for the quadrants, which goes through all the quadrants, and then we go top down now instead. So we're kind of mixing the two, like bottom up and top down here. But that's what we need to do in order to cover all the bases here, I'm pretty sure. I don't really have tests for this, except checking that everything collides with each other when you run it. So, whoops. Oh, and we got some compilers. Wait. Oh, I see. You are nullable or optional, so we'll unwrap these. There we go. Missing entries to pages. Okay. Yes, we do need to initialize, and this is actually with yes, you do need to have the type here, I think, because you have a catch. So yeah, this was this type. And this is, I guess, initial entries. Which is 1,000. Okay. That's not bad. Alright. It's just 1,000 pointers, that's fine. Okay, now let's see. Okay, there we go. Oh, we got a crash. Interesting. Okay, this one is out of bounds. Oh, okay, well, I guess instead of doing this, we could use append assume capacity instead. Because that would do sort of the same thing, but it also increases length, which will prevent, yeah. Okay, prevent the thing from happening there. The out of bounds thing. Okay. Yeah, it also sets the items. Okay, what now? Hang on. Okay, I think I need to do this here as well. Resize. Wait, this doesn't make sense. Why are we allocating and then Maybe. Okay, yeah. Okay, yeah. So we're allocating capacity. Then resize never deals. Well, it changes the length, I think, back to 0 or something like that. So it never messes with the allocation, unless you're resizing it to more than the capacity. Page is not equal to null. Bottom up. Oh yeah, eventually we are going to the root, but when we do that, the parent should be null, so it shouldn't go into that. Alright, we're going in here. We're checking if we have a parent, which means we're checking for null. If it's not null, we capture it, we go in here, the parent, and so forth, until we reach root, which parent is null. So really, I don't understand why, except this happens over here. I mean, I guess if this, I guess, okay, let's just guard against this. If we have a page, we will do this. There we go. And here you can see that we are building the tree. This is the quad tree. And we are colliding and... Alright. The little square that's moving around, I'm controlling that to do things here. Okay. And we got a leak. Oh yeah, so... entries to pages. There we go. Okay, so we got 202 bodies there. So the number of bodies depends on, you know, the efficiency of the algorithm, because it's checking for the FPS. Like if the FPS is high enough, we spawn more bodies. So depending on how efficient your algorithm is, it's gonna spawn more bodies. Is how I set it up. So if we change, we can measure this now a little bit, like very rudimentary here. So we change this to the other algorithm, to top down. Whoops, or just intersecting, because it's actually let's do this. Let's comment you out. Okay, how many? I mean, it doesn't look much of a difference actually. Still 202, so there's no difference. Okay, great. Okay. I mean, that's interesting actually. I mean, if we look at the quad tree, it's pretty large amount of quadrants, you know, and then it means like for each one, like it's gonna check. If we start at the top, we're checking first the top. Are you intersecting the top? Yes. Are you intersecting any of the blue quadrants? Yes. We're checking as of everyone. I guess we also bail out if we find one. So, you know, if we're lucky, I think the FPS will drop a little bit if we go down here. I think it's like biased. No, maybe not. It is so. I think it's like biased to the top left, maybe. I don't know. It starts there. So if we find this one, it doesn't check against the other quadrants. So if we top left, then it goes to the subdivision again. So I mean, it would make sense that we would be more efficient to go bottom up. So that's why I'm a bit confused. It should be more efficient, but maybe it just means that this part of the code is so it doesn't really matter that much. Maybe, which is strange, because I thought that this was the bottleneck right here. I could turn on tracing and do the whole profiling thing, but yeah, because we're looking for, like, top down, we're looking for through each quadrant. And yeah, we have like so I'm trying to calculate like the optimal checking order of the quadrants. I'm going through each one, and then I'm checking one quadrant at a time, right? But if we find, wait, what the hell is this? Wait, okay, my brain just, why are we calling this here? Wait, why are we calling? Oh, I see. Okay, yeah. So we know that we... Okay. Okay, yeah. Because this one, okay. If it doesn't intersect, we return. Okay. So basically here we're checking for intersection in the quadrant. But we also check contain, so that's weird. That's like a double check. This should probably return like a bool then, like if it intersected or not, if it went further down or not. Yeah. Return false. Return true. Returns true if page intersected ABB. If this is true, we return. No, wait. Wait. It's different. It's different. Oops. Because this checks contains, which means AABB needs to be fully inside of the quadrant. If it's fully inside, we don't need to check any other quadrant. That's the thing. Here it only checks for intersection. Like it could be outside, partially outside, partially inside. Okay. I was seeing this and I was like, wait, this, at first glance, this looks inefficient, but then I was, yeah. Okay. Yeah, so we're going, yeah, okay. We're bailing out, yes. So maybe it is kind of efficient anyway. Maybe it doesn't really matter that much. I mean, in theory, bottom up should be more efficient. I don't really understand how, like, it should be at least skipping a few checks. But yeah, maybe this is not, you know, the actual bottleneck in that case. Okay, so this whole stream has failed basically. I'm just gonna look at something here. I mean, the collapsing branches, that can still be a very nice optimization. Especially if you have like tiny entities. But I guess I don't really have tiny entities, so that maybe it doesn't matter that much. Well, maybe it's better to actually do a trace and profile the game and see what pain points, like what actual bottlenecks there are, instead of trying to guess here. I just thought that, well, maybe this would be more efficient, but maybe, yeah, I just failed, basically. Yeah. I mean, yeah, in theory, this should be more efficient, but in practice, there's no difference. Okay, and that's an example of why you don't prematurely optimize. Well, this is not prematurely optimized. Well, it kind of is. It's premature to actually finding the actual bottleneck, I guess. But it's not premature because I already have the library and stuff. Okay, anyway. Yeah, the collapsing branches, could still be theoretically an improvement, yeah. I just want to go through and see if I missed something here, because it just feels like it should at least do something. Yeah, this is the same function. So this is the function we're calling. And maybe it's the collision resolution that is the bad guy in this scenario. Well, as I said, I need to enable the traces to do that. Man, I should have the traces. I should have not like commented it out. I should have had like a debug. I should. What you do is you have like if trace, like is trace tracing enabled, and then put these in there, and then this one is like a comp time value. So in the actual, like if this is enabled, this is gonna run. If it's a comp time value, then it will get optimized away. This whole if will get optimized away. If you want to have like a release version. So this is this is the way I do it in the game code. Whenever I have like things like this. All right. Anyway. Actually, let's just do this. Let's just do tracing, I guess. Do I have like some sort of config? Yes. So let's set this to true. And we can import this. So I have like some sort of system here for my imports, but usually now I just collapse everything into one like this. Whatever, I'm not gonna change it right now. Let's see, and then we should have like, well, we can put it here, I guess. Is tracing enabled? Import. Do I have a config? No. I need to go back here and get this here. Okay. So now I need to go through every thing here. So I want to go C Tracy or and wait. Oh, also this should be like this. Come on. Butterfingers. Man, but I can't put this in an if though, because this will be a new scope. What the hell? I guess we can do this maybe. Oh. Oh no. Wait, how do you do this? I guess we can make it null and then do that. Okay. It also, I don't like tracing because it also like pollutes your code. It's so annoying, but whatever. No, not the fair. This would be like if prepare some. I guess it's fine. You could also do like you could make a scope. Nah. Man, every one of these is like this. I'm not sure if this is even a good pattern here. I just came up with this on the spot here, and maybe this will solve the issue. It's just so annoying also because you have like a million places of these things. And now here we can't do this either, so if zone and alright. Now I think this is like, because this is comp time known, right? And this is comp time known. So if this is false, this will become this value, which is comp time known. So this should also be comp time known. If this is true, then we also know comp time known that this is not null. So technically, this should all work out, like be optimized away, I think. At least in the case of false. Let's make this. Will it work? Yes. Nothing but a good old macro. Okay. That was that. I need to go to collision thing. Oh yeah, we have the build options. Oops. Oh, Z-trace. I don't have it. Where is it? It's just in. It's a dependency. Okay, so I actually need to go and find it. Zig Z-trace. Zig fetch save git plus that. All right, and there we go. Now we have Z-trace. Whole bunch of songs. Well, it's not. It was actually not that bad. Except this file is like What is AABB? It stands for Axis Aligned Boundary Box, I'm pretty sure. It's basically just a rectangle that is not rotated. That is like it's aligned with the axis, so and it's a concept. It's an important concept because it's very easy to check for collisions against other rectangles and points and stuff. So the idea is basically for the quad tree is that we reduce the problem. Sorry, I'm sneaking in a bit of Swedish there. Instead of checking, you know, if you have a circle, let's say, so you're not really checking the circle collision because that's a whole other algorithm. That's well, depending on what you're comparing against, it might be harder. If we compare it to a circle, it's actually pretty easy to check collision because you're just checking the distance versus the radius. But if you're checking against like a rectangle, for example, a circle against a rectangle, that might be more, you know, more complicated. So, but checking a rectangle that is axis aligned versus another rectangle that's axis aligned, that's super easy. So, if you reduce the problem first of checking rectangles, so let's say you have a circle, but you can reduce the problem if you make a rectangle that goes around the circle, that like that bounds the circle. So you have a rectangle that contains the circle, and now you check with this rectangle instead against whatever you need to check against. And if that collides, then you know that there's a possibility of the circle colliding. So basically, it saves you time whenever you want to do, like, you have a circle and you want to do a million checks against other entities. Well, if you first reduce it to a rectangle, that's going to be way easier to find the potential candidates for collision first with an AABB. And then check for the more complicated algorithm, which is the circle against something else then. Or a polygon, or, you know, any kind of weird shape you might have. Yes. Okay, we have the same pattern here, so let's go. Oops. Okay, that was it. Yeah. Alright. Yeah, it was only like intersections there. And that was everything there. Okay, we have ABB. Whoopsie daisy. Oh yeah, we need to import. That's right. We need to import is tracing enabled. Yes. And we need a few set you are like this. Here's the main function. There we go. physics. Let's hope this works as well. I don't even know if this is gonna work, because I haven't used this library in ages, so there might be some issues with the version here. I don't actually know if it's gonna be like compiler errors or something. Okay, is that it? Yes. Okay. So now we've enabled Z-Tracy. Yeah, but I don't think this is gonna compile actually, so don't get your hopes up. Alright, let's see what we got. Expected optional found stub zone context. Interesting. Oh man, do I have to annotate the type as well? Okay, I'll make a replacement. Let's do const equals if. This should look the same, so I'll just do this. What? Oh yeah, I need to capture it. Zone, and then we'll add a type, which is what? Z3Z zone context, and equals if is tracing enabled. Alright, does this exist or? Okay, this doesn't bode good here, because Z-Tracy, it can't see what the underlying types are, so I'm gonna guess this is not correct here, but okay. Main 16. It still says stub zone context. Oh yeah, it needs to be nullable. Okay, so it didn't complain about the type. So this might be correct then. Yeah. Wait. Yeah. Okay. Yeah, okay, so the only thing... Okay, so we need to... So let's search for zone or equals if is tracing enabled. Okay, so let's do this replacement, but we add a question mark here as well. Alright. Oh, you're done. Yeah, I think that's it. Yeah. Alright. Oh shit, it worked. I was not prepared for that. Okay. Right. Okay. Wow. Now I need to remember how to make this, how to actually access this now. Let's see. I think there should be like a server that you connect to. Also, let's, well, actually, let's double check if Tracy was enabled here. No. I guess true. Okay, here we go. Now it's doing something with Tracy. Okay, and there's less things there. Okay, how do I... How... Man, I had some kind of client for this, I'm pretty sure. I don't remember now where that was. Okay. I'm so close. Here, we're so close. Let's see. Because C tracing, it kind of uses like I think it uses like some sort of standardized tracing thing, and yeah, Tracy. Can you see this here? Why is it like... Oh, I see. There we go. So basically, yeah, this. But it's... but I did have a program. I just don't remember what it's called. Tracy profiling client. Oh, this is just this. Or is this the project that you... I'm pretty sure I have like a different program that I ran. Maybe we just download this one then. I don't know. What? There's like a bunch of exes in this one. I don't know, man. Profiler. Oh. Profiler. Wait, did I run it or not? No. Okay, now the thing is running. Wait, where's the other? Okay, which port is it using is the question. Because I probably need to open that port. Documentation. All right, let's see. Can you please Oh, it downloaded a PDF. Oh shit, mate. This is like old school stuff. Okay, quick look, first steps. I just want to know what port it is. Changing the port. No, I want to know. Okay, 80s. Okay. Thank you. And we go back here. I'm gonna there. Okay, and we open up a terminal, and it should be like no, allow that. Right, there we go. Does it work now? That's the question. Connect. There we go. All right. Okay. Okay, how does this work? Where's my traces and stuff? Pause. Resume. Wait, what did I do? Actually, you know what? Stop. Discard. Yes. I think somewhere, I think if you run it as a, because I ran it as a Linux thing, so I should run it. So there's like a sig, because yeah, I think there's some compatibility issues. So I should run. Wait, where's the Windows? Target. Windows. Wait. Okay, 1 second. Zig target Windows. Target. Oh yeah, you had to type something weird like this. Yeah, right. Yeah, okay. Okay. Yeah, I think you type something like that. There we go. Oh no. Oh, unknown. Okay. What if we remove this? This might be some weird cache issues. Maybe, hopefully. Come on. No. What? Are you serious? Unknown file type, trace client.object.o. What? It succeeded so far and then failed here. Hmm. I mean, I wonder if I have more luck like in Windows. But I want to check the version first. Okay. Okay. What? Okay. Let's do power. No, wait. PowerShell. Non-interactive. What the hell? PowerShell run command. PowerShell commands. Okay. PowerShell command. I guess it didn't need to have it. Okay. What? Man, why? Like, I have been able to compile Ctracer before to Windows because I've profiled it before. I do remember it's working. I mean, it might not be necessary. I don't know. That's a shame. Okay, let's try it again. We'll start it up. And connect. It's just, what am I looking at? Like, where? Okay, here we go. Well, I guess this should be enough. Let's see what's happening. Physics update. So it takes 21 milliseconds. Yeah, that's like, I mean, it's not 60 FPS. I think 60 FPS is like 17. Alright, what is taking time? Add pages. Populate and intersect add pages. So add pages is what takes time, it looks like. And then resolve collisions. Okay, this doesn't actually take that much time. I mean, we don't have that many collisions, but for this simulation, add pages is the thing that takes a lot of time. This is weird. It's like, okay, Oops. So add pages. Self time is 30%. Let's look at a slice here. So we got like inserting into page. Yeah. Got so many calls down here. Maybe if we make it into a loop or something. I mean, it is recursive, but we... Okay, can we go here? 200 nanoseconds, that's pretty good. 760 nanoseconds. Self time, how does this work? Oh, it's 100%, okay. Yeah, okay, that makes sense, it's in the bottom. And here's like the intersection part, that doesn't take long. That's one ABB intersection takes about 150, 160 nanoseconds. Yeah. So basically, we're doing these inserts. So yeah, you can also see that obviously but you can see here that the insert takes about a third or half the time of the intersection check. So the intersection check actually is the bottleneck, which is surprising to me. Okay, well, we can, I think maybe, can we keep this? Can we store this? Save trace. Okay, let's save this as bottom up. And let's go back here. And we'll change this out to let's change it. Where was this? Quadri. Run it. We will discard, reconnect. Now where are the things? There we go. Okay, so let's stop. Go here. Okay. Now this is interesting. You can see already how they go way deeper now. And now I don't remember how long this took. So about 2.5 6 milliseconds, something like that. Well, it also depends on how many bodies there are, but I think there's like the same amount of bodies. Like, yeah, probably. And there's still kind of the same ratio between insert and intersecting here, but you can see, I think it went further down this time, I'm pretty sure. Because we're going for the top. It also depends on how many subdivisions there are, yes. Like how small the bodies are. Like if I decreased the size of the bodies, that will increase. This will increase. Like let's actually redo this. Okay, I'll save this as top down. Hang on, top down. Original. And then we'll quit. Go back here. I will go to main. And we have these things. Where's the... Yeah. Add bodies until lag function. This adds rectangles in random size, random radius. So random size, random radius. The radius is determined here. 10 plus 5. Actually, this is not used. I guess it's used here, but this is not used. Or is it? Yes. Okay. Well, I don't know. Anyway, if we change this now to like, I don't know, radius, let's do like 1, just to have like an extreme case. Okay. Now let's disable. What's the problem now? Unused. Okay, let's disable say tracer for a second here. You can see now these are like very small, and if we go into the tree visualization, you can see that they are so far down into these trees. Like some of these trees are super small. So, and if we go to the bodies, we can see that there's only like 102. Like that's half of the bodies that we had before. I mean, I could add more, I guess. We have about 40 FPS. Okay, now let's enable. Let's say, well, first of all, I want to change the algorithm to bottom up and run this again and see what the result, like what the difference is. Okay, now we have 202 bodies, so actually this is more efficient. Haha! Okay, you didn't see the thing. What? Yeah. Okay. Here you see. You can see, and we add a new body here. You can see that. Yeah. The number of subdivisions is very big there. If you put it in like a corner, that's the worst place it can be, because that creates like the most amount of subdivisions there. All right. And there's a yeah, so this is more efficient. Okay, finally, I got it confirmed. I mean, okay, it was pretty efficient, I guess, from the start, but this is more efficient. At least it's at least as efficient, I would say. So that is that is not a fail. This is a success. Well, it may not be the largest success, but whatever. It is interesting. Let's see. If we go back to here now, so oops. Well, as I said, as you can see here, like the insert takes about 6 microseconds. The intersecting is about double the time. And yeah. Why is there so much time like in between here? Like if these sections were shaved off, this would be nearly, not nearly, maybe it's like the boundaries between the function calls that takes time as well. Could be. Okay. Well. So it was pretty well optimized, I would say. I think if we manage to build the tree in such a way that searching takes less time, we have to also make sure that actually building the tree doesn't take too much time. I actually thought that this would be way more like insert. Okay. Also, here you can see add pages, populate and intersect. So why is there so much time between here and there? I don't know. Add pages has like a lot of self time. Add pages. Where is that? Is it this that takes time? Add page prepared. No, we have a zone for that. Oh wait, this is also a. Oh, this is add page. Okay. Wait, is it add page or add pages? Okay, so that's add pages. Oh, add page barely takes any time. It's like 350 nanoseconds. Okay. But add pages, 24% self time. This is add page. What is taking the time here? We have a loop. We call this function. Maybe we should put a zone there. I don't know. We append assume capacity. I mean, append. This should be assume capacity, to be honest. What the hell? Yeah. Why is it max entries in page times 10? Let's just make this initial entries capacity. And then here we assume capacity. what difference does that actually make? Like, the only thing, like, it's checking for capacity and then increasing it if it's not. Also, we probably don't have any orphan entries, so it doesn't really matter as much. Intersecting, this should have its own zone, yes. And then the intersection handler that actually has, that doesn't have a zone. Maybe that's taking time. We should put a zone there. Zone, sorry. Intersection handler. That should be like collision. Intersection handler. Populate and this guy. Do you have a zone? No. Okay, so do we have Z trace in here? Yes. Let's grab that. Put a zone in here. Intersection handler. Let's also make it a color. I think in AABB we have a color here. Zone and C. Let's make it yellow, whatever. Okay. Okay, now that should be visible. So what did we do? We did something. Yeah, we changed this to append assume capacity, that's fine. But everything else was basically zoned, so except for, I guess, this, like get entry ABB, which is what? Is this like part of the... No, this is the wrong tree. You are barking up the wrong tree. Let's see, this is quad tree. Get this one. We're doing a cast, that's no thing. And then we get, so we do a get from the register. That should be like an O1. It could be out of memory cache, but yeah, we have to get the information to be able to check for collision. That's always going to be a problem, I think. It's like the locality of the positions is never guaranteed to be very close unless you... I've thought about this as well. It's like arranging the bodies in like a, what's it called, like a Hilbert curve style thing, where you have a one-dimensional array, but it's encoded in such a way that it's elements that are close in the array is also close in a two-dimensional space. But yeah, well, probably close in a two-dimensional space, I should say. Well, no, actually, if you, yeah, but the entities that are close in the array are guaranteed to be close in the two-dimensional space, but entities that are close in the two-dimensional space are not guaranteed to be close in the one-dimensional array. And it kind of has the same problem as the quad tree with the boundary, the line, there's like boundary lines. Or, I mean, yeah, there's some... Okay, well, anyway, that's a whole can of worms there. But anyway, so let's see. But that just feels like too much optimization. I don't know. This is I'm pretty sure I'm good with this. Let's just do a run here. I just want to see what is taking the time. Wait, there's an error. Oh yeah. Yeah, the append assumed capacity does not need to get. Hang on. Connect. Discord reconnect. Yes. And stop. Oops. Update collisions. Populate and intersect. There's still no. Yeah, intersection handler. Okay, so that's also very fast, I guess. It does fill in the gaps a little bit. I mean, it does take time. It's not super fast, actually. It's pretty slow, to be honest. Actually, yeah. Okay, it does fill in the gaps here. But I was thinking about this gap over here. This, like, giant gap over here. But I guess that's just a one-time thing. Or, I mean, not really a one-time thing, but it's, I mean, not guaranteed to be a one-time. I'm not sure what this is. Like, where's this big gap over here? Maybe I need to look at this part instead. But, yeah, the intersection handler actually takes more time than I thought it would take. Oh, is it, like, divided up now between intersection handler and intersecting? Oh, interesting. Interesting. So I think maybe this was part of this before. Perhaps. Okay. But why does this take so long? Let's check. Let's check that. Also, just to be sure, I'm gonna actually make a zone here. This is gonna be get AAA baby. Yellow. Wait, is this yellow? Yes. Okay. It's like, is the first one alpha or the last one alpha? You never know. I mean, I guess usually the last one is alpha, but okay. Get AABB. Yes. There we go. Okay, cool. Yeah, I am very curious actually. Let's restart this. Oops. Reconnect. Stop. It doesn't show up here. Oh, it fills in the gap here. Okay. So there you go. I mean, it doesn't take that long. It's just that this is happening for every entity. Yeah, so there's like 100 or 200 of these instances, which is what takes so long. But then you also have these gaps. I don't really know what they are. Like resolve collision. Okay, it's these ones, I guess. Resolve collisions take time. Update positions takes 100 microseconds. I mean, I guess compared to this, it doesn't take that much time. Okay, but why does this take so much time? It's just, I mean, this is also, I think it's because of it needs to fetch from memory. I think that's why it takes so much time. I think because if you look at the code, all it's doing is well, we're creating the traces zone, but that shouldn't take too long. We are getting, well, we're casting this to a register, which should take no time because it's just a cast of a pointer. I think maybe there's some kind of plus address going on, but it shouldn't take that much time. And then you have body get. So this should be an O1. However, we're probably accessing memory that's not loaded in the cache right now. And then we are returning this position and size here. Actually, this has a bunch of other stuff as well. This has like, well, we have 2 vectors. Actually, it's not that bad. 2 vectors and a bool. So 4 F32s and a bool. Okay. I mean, we're just returning a value. But it takes like just as long as to, what was it? Like this, it takes almost as long as the entire intersection handler to just get this value. So yeah, we're operating in very small time frames here. But it does need to do this for everyone, yeah. It adds up. Each frame is like, actually, what the hell? Oh yeah. That's also another thing. Each frame is 20 milliseconds here. It does this update collision. It only takes 2 milliseconds, but we have to do it like 8 times or something in order for for collisions to have a good precision. So the more the basically we're dividing the physics update into smaller time segments and doing a more precise collision update. That's why we have like 1, 2, 3, 4, 5, 6, 7, 8 of these collision checks, and each one only takes 2 milliseconds, but summing it all up, it takes 20 here. And each time we have to resolve collisions, and we have to update positions, and again update collisions. Actually, yeah, we're populating the entire tree, and maybe we don't need to maybe we don't need to repopulate the tree every time, because there's gonna be tiny changes unless you have like something that travels at the speed of light or something, but that's only one entity though. But if we don't update it, then it might be out of date for some of the... But we could do... we could actually have... okay, like when you are checking for each entity that is colliding against other entities. Right now we are going... Yeah, we just assume that it's in the correct quadrant, but it might not be. Like if we don't recalculate the quad tree, we only calculate the quad tree the first time, and then subsequent you reuse the same one. Now, what we need to do though is we need to, for each entity that we check, then we need to check that it's still inside of its quadrant. And if it is, then we do things as normal. So that's one extra check for each entity. But if it's not inside, then we have to sort of put it at its parent's level and keep going that way. Yeah. That could be something. Because then we still have to do this 8 times, but we won't have to build the entire tree every time. Although, as you can see here, building the tree is actually like only, I don't know, 1/6 or something of the time. Actually, this one was way larger. Why is that? Okay, some of them are actually larger. Oh, it's the first ones are maybe... Actually, maybe it's like half the time or a third of the time. So we will basically cut maybe a third of the time if we do that. That is interesting. Okay, that's an idea. Yes. Okay, that's gonna be a goal. Okay. Yes, we've got it. Bottom-up search is good. That's very good. Collapsing branches. We couldn't get to that. I will add another one. Whoops. Another one called... so this one is gonna be... no rebuild insane frame. Okay. I'm just gonna BRB 1 second. I'll be right back. We'll try and figure this out. I just thought also, as someone saying in chat, like we might also figure out a way to utilize vectorization for the quad tree, but I don't really have a good idea on how to do that. But it is an interesting idea, because that, if that could be utilized, that could save a whole bunch of time. Because basically, I mean, the way we do like updating positions, that utilizes vectorization, and if you disable the collision system and just add as many bodies as you can into the system, like right now I could get like I think it was like 150,000 entities without lagging into the system, but I know that it's possible to get even more, but I don't really know how right now. But I mean, it's way more than I will ever need for my game. So I'm happy where it is right now, but yeah. Okay. Anyway, quad tree. Yes. Okay, no rebuilding same frame. So basically, we want to have a separate algorithm for subsequent in the same frame, like for so we have one algorithm for the first run, which is the one we already have, and then we'll have a separate algorithm that is only for if you already have a tree and you want to run an intersection again. So where is that? Here, where is that? Collision no, not collision container. Quad tree. Right, so we have populate and intersect, but we basically want to have the same thing, except it's not populate, it's only intersect. So basically intersect it's gonna be the same entries. It's gonna have the same everything. Okay, I'm gonna just call it intersect because we have populate and intersect, and this is only intersect. So this will be only intersect. And it's not pi zone, it's I zone. Welcome to the I zone. Okay, we don't reset, and we don't even need to change the context we already have. So we don't need this, we don't need any of this. We already have the boundary, we don't need you. I'm not sure if we need the allocator, but we'll see. We don't need to calculate the prepare the pages. We don't need to add any pages. We do need to get the entry ABB, but we don't insert or add things to lists. We only check intersections, and we run the intersection handler. But now also this should be self entries now, or actually wait, is entries guaranteed to be? Yeah, okay, so entries yeah, that has to be like guaranteed to be the same index. I'm pretty sure. So actually we could grab where am I? I'm at populated intersect. So if we just go through entries, we get items. We get the entry A, B, B, and we also have the I. Okay, so the entry is, and the entry should be entry values I, and the A, B, B we already have. We don't insert anything. We have intersections. Right, so now we need a different algorithm for checking intersections. So basically, I mean, we still gonna use this, but we need an intersecting how would you call this? So basically, I just want to check if the entity is still, since we're working with a dynamic system now, we want to check if the entity is still in its quadrants. I'm gonna call this dynamic just to be fancy. Alright, so we have, let's also make a zone for this here. This is intersecting dynamic. Wait, did I not say bottom up here? Intersecting. Okay, whatever. Intersecting dynamic, and this is like 4-page. No, it's not 4-page. Okay, so we get the page. What? Oh, I see. We do this. If we have a page. If we don't have a page, we're an orphan. So then okay, hang on. Now you are, this is populated intersect, this is intersect. We need to call dynamic here. Okay, let's see. If we're an orphan, well, if we're an orphan, I think we just call intersecting bottom up. Hang on. Here we're also doing this. No, this doesn't make any. Okay, whatever. Let's just copy all this. Let's make an entirely new thing. So yeah, so if we have a page, we want to check if we're still contained in the page. So if page contains AVB contains AVB, then we still do this. Then we do the normal thing. Otherwise, this means we have moved far enough to not be contained anymore. So in order to have a precise collision detection, we need to do this. And we need to then basically you have to go up the entire tree until you find the containing page. So we could write a function to get that page. So and then let's do this. So let's do containing page, get containing page, and we'll have like the ABB and then the starting page, which was page. Actually, it should be like page.parent, I guess. But that might not even exist. So actually, you know what? We could get the containing page like this. Yeah. So page is that might or might not exist. The containing page, we get the containing page. Now if we make this except a nullable or an optional, we can do that. Okay, so we get the containing page. Now this might not be this might be null as well. So if it's null, that means we're an orphan now. So we went from having a page to being an orphan. And I guess if that happens, we need to basically do a brute force. We need to actually put ourselves as an orphan now. Do we want to change things? No, we don't want to change things. Actually, this doesn't work. This does not work. The whole premise of this doesn't work. I just realized. Because even if, like, okay, we're going through each entity, even if for only that entity we kind of, you know, optimize a little bit, but the next entity cannot actually find this entity. Wait. No. No, this is bad. This doesn't work. This doesn't work. No. I'm gonna cut my losses here. Yeah, okay, now that failed. Because it's the same issue also with the collapsing branches, because when we're while we're populating the tree, we're also checking for intersections. So it's a very efficient way to prune a lot of checks that you don't have to do, because the tree has not been populated yet. So you're skipping like double checks and everything. Yeah, no. No, that's worse. Man, I was just thinking like, man, we already have the tree. Maybe we can like reinsert? No, that's just like rebuilding the tree. Because we have to do it for every entity. Well, okay, wait a minute. We could okay, wait. Actually, we could utilize so we're utilizing the fact that in each like subdivisions. Okay, now we're talking about subdivisions of the physics update. Right, there's 8 updates. So there's 8 divisions of the frame. So there's 8 like collision updates every frame. And we're utilizing the fact there's a tiny time updates between those frames. So probably things have not moved that much between each update. And so yo, Noctu 4, how's it going? It's going good. I'm doing a little bit of premature optimization. No, yeah, we're doing a little bit of optimization of the quad tree, of the collision system. Yeah. I mean, it is fun if you enjoy it. But I do enjoy a little bit of a puzzle, programming puzzle. So what are you up to? Let's see. So yeah, there's tiny differences in position, so they probably have not changed. So we're utilizing the fact that there's a large chance that they have not changed containers. So here we're checking, okay, which is the page. We want to check if, okay, first of all, do we have a page? Okay, do we have a page? Unless if we don't have a page, we're an orphan, so it doesn't matter anyway. Then actually, if we don't have, then we should do a top down. Then we should just return a top down. Yeah. And yeah, if you're orphan, yeah, but then okay, whatever. Wait, page. Oh, the page is actually the page. Wait, what? I thought we got root from there. No. Okay. Yeah. That makes sense. That should also happen here. I think we didn't run into issues because there was no orphaned things. Alright. Nice. Let's see. So we got the so okay. Hang on. Okay. So we bail out with the root, the top down there, yes. So actually, yes, here. So if we have a page and it still contains, then we just do the normal thing. Yes. Otherwise, actually, if this does not contain AVB, no, we have to do this first. We have to do like an update first. Oh, Yeah, we have to loop through the entities multiple times. I guess we can try it. Doesn't hurt to try. Except it takes precious time. Okay, let's see. Yes, intersecting. Very good, very good, very good. Intersecting for top down. Wait, what the hell is this? No. Here we go. Intersect. Yeah, we have to go through each one. Okay, so basically we're doing this. We go through each entry. We get the page. Entries, 2 pages. Right. So we have that. So now this is the I. Now if page contains this, we're good. But if it doesn't, so let's you continue. If it doesn't contain, then we will yeah, now we have to reinsert. Yeah, we have to reinsert the entry. We have to yeah. Okay. Yes. So first of all, I'm gonna set you to null. Actually, that's inefficient. But anyway, I'm just gonna. What's happening here? And then the page that you're in, we should remove you from the entries. Yes. How? But we don't have you in here though. Actually, I guess it could still be in there. It doesn't really matter that much, I don't think. It's not gonna, I don't think it's gonna happen that many times. The problem, like, if we don't remove the entry from this page, it just means that sometimes we may do more checks. Maybe it's better to remove it. So, page entries length j if page entries j is equal. Wait, this is an index. Yeah. If it's equal to I, then ooh, but we can't just remove it. Damn it. Okay, then let's skip it. Let's just skip this. We just have to live with that. Okay, so basically now we just reinsert. Yeah, we do insert. Now we can't really do any assumptions of where it could be. I don't think, because I mean, it's very close to where it was, but it might have crossed the boundary into the middle, for example, and it's a whole other quadrant. I mean, I guess technically, yeah, actually, we could just check the parent. Yeah, actually. Actually, we just put it in the parent, right? That should be good. Yeah. Yes. Unless the parent is, unless we're in the root, then we get orphaned. How do we do that actually? Where's, we just add it to orphan? Okay. Okay. So if, okay, so we don't do this. So we do if page parent. So that means it's not the root. Then we insert into page parent. We just insert it to parent. That's fine. I think that's what we could do. Maybe, no, maybe not actually. Well, okay, no, actually no, that doesn't work because let's say you're in the center, like very near the center of the map or the center of the space, and you move a tiny bit to the right to cross over the x-axis of the center of the entire boundary and of the root. Then you have to basically bubble up all the way to the root. Yeah. So yeah, so basically we could do while, maybe while this exists, if we contain, we continue, so this is like update entities. Yeah, sure. Okay, so if we contain, we will bail out, but otherwise we set this to the parent. Okay. Well, how do we do this now? We don't want to insert in every stage. We just want to insert when it's done. Okay, let me do this. Let's say like original parent is this. We still want to do that though. And then here we're gonna say if original parent is not equal to the current parent, which is this, then we do insert. If it exists, I guess. If then we get the new parent, I guess, new parent. And we insert this into the new parent. This will be I, and this is entry. Okay, if the new parent is the orphan, then we're gonna do append there. All right. And this one back here. Actually, I want to check this. No, I don't want to insert into quadrants. Actually, I want to do this. Oh man, but if it can't accommodate. Okay, actually, let's do like insert into page if can accommodate. Right. Otherwise, I guess we'll orphan it. Or it goes further up. No. No. Actually, let's keep that. Let's actually do another check here. If it contains and if can accommodate. Right, so now we're guaranteeing that we can accommodate. And basically can accommodate is just that we can have 10 entries in each page, and if the current length is less than 10, then we can accommodate. Okay. Now, where are we? So, we update entities, original parent, we are... Right, we're bubbling up basically to check which one is containing and can accommodate us until it's null. If it's null, or well, if it's not equal to original parent, we check if the new parent is not null. Then we insert it with the knowledge that we can actually accommodate. So basically we should just be able to do this. We don't need to do that though. Let's just do this to make it super more efficient, I guess. The page new parent, yes. Why am I not getting... You're a page. You're a slice. So this should... Okay, whatever. Okay, and then we append that to the new parent. Because there's no way that the entity would go across the entire boundary. I don't think. I mean, if it's a very small entity and it's a very fast, this is like 1/8 of a frame of difference. So because I was thinking like, okay, well, technically it could have passed the boundary to go into another quadrant that is deeper down, but it doesn't really matter that much. Yeah. Anyway. Otherwise, we also, we add it to our orphan entries. Oops, that's some JavaScript over there. Okay. Now. What the hell? How do we tie this up now? So we have, we're updating it. So basically we have a dynamic tree at this point, because we're calling this one with an already built tree. We're kind of assuming that the entities won't change much. So we're updating them just in case here, and reinserting them into new quadrants if they need to, and basically finding the parent that could accommodate them and contain them. Okay, but then when we're done with that, then we go through everything and check for intersections. But now we're using intersecting dynamic, but we really don't need to. We could just use bottom up actually. We could use bottom up. The thing here though is that we could also skip entities that already have been checked. I'm not sure exactly how much more efficient it will be, since we're not like going through the, it's not like a brute force algorithm where you loop through the thing twice, or a nested loop. This is more like you would have to pass some sort of list around where you have, well, we could have like a binary checkup maybe of which ones we've already done, but that seems inefficient as well. I mean, I don't know if that's gonna be more better. I don't know. All right, see ya. Have a good one. So let's see. Intersecting bottom up. Intersecting. Yeah. Okay. Okay. I'm not sure if that's actually gonna be better, because the thing is, yes, we're not building the tree each time, but now when we're intersecting, we're checking against, we're doing a lot of double checking. Okay, well, let's just test it and see, I guess. Okay, so now the thing we have to change is we need to call this function instead of the other function. So the first time we want to check, we call populate and intersect. Next time we want to check, we call intersect instead. Okay. And we basically scrap this whole intersecting dynamic. Okay, there we go. Context. Oh. Right. Wait. Well, I guess an easy fix would be just to add this parameter here, I guess. No, context. Actually, we might need this context. Yeah. Entry. No, that's, wait, entry. Yeah, that's I. Yeah. There we go. Okay. So, yeah. So now we go to the physics system. And update collision. So yeah, we have to say, we have to have like options now here. So options, actually we could put, yeah, let's just do check collision qt options. So boundary, we don't need boundary if, actually this could be like a union enum, and this would be like build and check. Boundary. And the other one would be just check. Right. So this is options. And yeah. So here's like if or we could do switch on options. If we have build and check, otherwise known as back, we do this and back.boundary. Okay. If we have the other one, which was just check, we will do a similar thing, except now we just call intersect, and this one takes the context, which is, I think, self. There we go. Yeah. All right. Now back here. So now we have to pass options. So let's pass this along here. This would be collision container qt options, and we'll pass this over there. Right. Now, oh, we need to pass this here as well. Well, this one is interesting. Like, okay, I think because the thing is, we have this physics sub-step here. Sub-step. Let's pass the sub-step in so we know if it's the first sub-step or the whatever sub-step there. Wait, what's this? Dynamic sub-steps? I don't think we call this. No, this is like ancient history. Okay. So this one will take sub-step. And right, so here we'll do if sub-step is 0, so the first one, oops, then we will do build and check. Boundary is self.boundary. Otherwise, we will do check. Pretty sure you can format it like this, and it will keep. No, okay. Well, we don't return this anyway, so we can do this. Actually, you could also do this. This is like a nice trick here. You can add a function to the union enum, where you could say like build and check. Let's just call it build, whatever. And then you just pass in something here, boundary, and it will return this. Return build and check boundary. So it will. It's a nice. It's like, yeah. If you don't have, okay. If it's not a quick enum like this, and you have to like build an entire struct and stuff, then you can have a function, because that's way more terse when you call it. So here, well, let's go back. Okay. So now instead of this, you do build, oops, boundary. There we go. way better, I think. Wait, what if we do this? Aha, there we go. Okay. Okay, so basically the first substep, we build a tree, and then subsequent substeps, we do like a dynamic update and a check. But since the update is pretty far, or I mean, since the entities probably haven't moved very far because this is a physics substep, then they probably don't need to recalculate a lot of the tree. So it's probably not a huge thing to have a dynamic check here. And we don't have to rebuild the entire tree every substep. So let's see if this works. We gotta compile the error somewhere. What are these errors here? Never seen that before. Maybe it's because of the windows. Oops. Let's remove the cache. Okay. No. I don't know what the hell's going on there. Okay, 454. Right. Root. There we go. 240. You are you're K. Okay. Well, that means. Well, that just means. Yeah, that means entry values. Alright. Or item sign? No, just I. There we go. 294. Expected type list. Hang on. Okay, wait. Top down. Where's the orphan? I guess we don't do it here. Do you do anything other weird stuff? No. Okay, fine. Yeah, okay, so this should be good. There we go. Okay, well, I've got a crash. Oops. What's your problem now? Index out of bounds. What? How can there be more? Okay, now I am confused. Now I am confused. How could there be more in that list? We're going through each one and we're appending things. So there should be equal amounts in each of the lists. This one is just a duplication. What about self.entries? When do we actually populate that? Insert into page. Okay. What about orphans? No, but that's... Oh, hang on. Wait. No, but we're resizing it. It's initialized with capacity. We're resizing it to 0. Yeah, this does not make sense to me. What? Okay, so it's not called. Wait, so when is this set? Like here we're only setting like it's already it's already the length has already been set here. So where are we extend? So here we go. Right, prepare to add page, right. Okay, so there might be more entries here than in the actual number of entries. Because we're saying number of pages, which I think is like the pre-calculated number of pages, which might not be correct. It's like a high guess to be able to contain everything. And then, actually, you know what? Oh yeah, we're resizing. Right, so we right. So we already may have resized. So we're not deallocating these, everyone. So we might not do additional, like we don't do allocations each time we do this, basically, because that can't take time. So, but this one, right? So we're doing this. Okay. Now I understand. And what I want to do then is here we don't actually go through it like this. Then we have to go through entries to pages actually. And we get the original parent there, and then we get the entry A, B, B from entries like this instead. Okay. Still some issues. Still out of bounds. 246. Oh, it's the same issue here. Well, let's just go through entry values, but that one I think is yeah. That one is that should be fine. All right. Okay, there we go. Cool. So let's go to trace thing, reconnect. Send me some traces, please. There we go. And stop. All right, let's have a look here. Okay, so okay. Well, you can clearly see now. Well, I mean, update collision 4.32 milliseconds in this instance. That's a bit high for, I guess, the mean here. I don't know. Let's take this one, I guess. Update collisions. Wait. Positions, collisions. So here we do like populated intersect 4.26 milliseconds. This 3.454. So that's that's a lot lower. I mean, not a lot, I guess. It's a small win, but it is a win. Why is this like double here? 406, 803. Right, because we're not inserting, that's right. We're not inserting, but we're still doing intersection. Yeah, so we're skipping the insert and get AABB. I think also, yeah, we're actually skipping that as well. You know what? I just had an idea. Maybe it's faster if we just loop through once to populate ABB instead of yeah. Wait, is that faster? I mean, yeah, okay, let's try it. Okay, this will be the last thing that I do here, so but it is a tiny bit faster. So this one did not fail actually. This one was actually success after some adjustments. Okay, let's add another one, which is what was it now? Oh yeah, so pre-copy ABBs. Okay, well that's fairly simple. We just need to do it in the first stage here, populate and intersect. So somewhere here, like here we're going through all the entries, but let's do it again. Should we add a zone for this to see how long it takes? No, not in, outside. Pre-copy zone. Pre-copy ABBs. If alright, then so in here yeah, we'll get the thing. And copy it. I wish this seems like a good way to, like a good place for vectorization. I'm not sure if that exists, like turning a loop into that. And I think, I'm not sure, the AABB is, well, they're actually oh, whatever. Let's just set this to be where is that? Entry values. No. Entries equal entry ABB. I think also there's some value to, like, I think sometimes the self.entries is actually not set sometimes, but that seems strange though. So we don't need to set that. Okay. Yeah. Let's see if this does any sort of difference. Oh. Oh. Let's see, entry. Now this needs to be entries. Oops. Oh, hang on. Man, this really becomes, you kind of get blind to all this text here. There's the structure here is really bad. I mean, I wrote it, so I can say it. Okay, so that one is there. Okay, and now this happens crucially after we've increased this length of this here, so it shouldn't crash because of out of index arrays or whatever. Okay. Okay. I mean, just have some reference points. This ran like 813 times. We have, this took 1.35 microseconds times 800, so about 1 millisecond or something. I guess that's not bad. It just happens once. Let's see. Let's do discard, reconnect. I'm just curious if this is faster. Because now we need to loop twice. Where are they? There we go. Stop. Well, it took 500. Pre-copy ABBs. Yeah, you can. I think you can clearly see. I think here they are probably like adjacent, maybe in memory. Here it needs to fetch something. I'm gonna guess that's what's happening here. I think it's better to do it like this. I mean, it doesn't save that much time, but actually, I want to check how many bodies do we have. 203. Okay, that's an improvement actually. Because when we didn't run tracing, that's how much we had as well. Wait, we're still calling get AV here. What the hell? Wait, what? What? Oh. Okay. There we go. Oh, what the? What? Oh. Sorry. Items. Okay. Now let's see. Discard, reconnect. And stop. Okay. How many bodies? Still 200. Okay, update position, update collisions. Hopefully, wait. Yeah, this is the first one. This takes like, I mean, it's kind of the same. We save like half a millisecond, I think, on that. Well, maybe a bit more actually. Yeah, half a millisecond, like on each frame, like that. I mean, yeah, it's something. Okay. Why does this take like so much longer? There's a big difference here. There's like, I mean, it's like almost 50 times. Or no, wait. 20 times more. I'm gonna, yeah, I'm gonna, it's probably something to do with loading memory, maybe, I don't know, like caching. But it's just weird. Is it consistent though? Not really. Yeah, maybe it's a necessary evil, I don't know. So also I think if we could get rid of like a lot of these, like maybe if we didn't do this recursively, if we did it in like a loop, maybe it would be better. But I'm not sure how to unroll this loop because it's like recursive. Or not unroll, but you know, I guess unrolling the recursiveness into a loop is what I meant. Not unrolling a loop, because that's different, because then you know how many iterations you're gonna do. Maybe you can loop through each like each layer, but then you have to like keep track of subdivision, like each subdivided thing needs a separate like set of variables. I mean, it might be possible. I think that might optimize something, because I think that every time we call a function, that is taking time. I mean, it's not much, but it's a lot of function calls over a lot of, like, each of these is a lot of stuff. Especially if you add more entities as well. So maybe getting rid of a lot of these function calls might speed up things as well. Okay, well, 40. Well, it okay, yeah, I think it jumped up because we could fit more bodies in, because it detected like less lag. So I think overall this is a win. Very nice. So we got the trace thing working, so very cool. And can add a bunch of bodies here. I think if you add bodies like in the center here, it's gonna be, it's gonna lag it down a lot, because that's basically adding bodies to be brute force checked. Okay, what if we disable the tracing? How many bodies do we have? Still 200. Let's add like uniform set. Huh. You can see the collision result. This resolution is kind of weird when you have those small bodies. It doesn't look perfect. Yeah, that's weird, and that just went straight through. Okay, maybe that was a circle. Okay, well, I guess this saved us. Okay, let's just write it down, like saved. I don't know how to call this. I mean, it depends on how many bodies and stuff you have, but it saved us a very small amount of time. Saved a very small amount of time. This I mean, I think this one did save us more time, the most time actually. I think this one saved us a lot of time in certain circumstances. I think this was a win in a lot of scenarios, but also like, yeah, save time in certain scenarios, I guess. Which was, I mean, I don't remember. And then this one, no rebuild the same frame. Yeah, this saved save time. Okay. Well, anyway, that's gonna be it for this time. Just a bit of fun idea that I had to dive into the the quad tree code and optimizing that a little bit. But yeah, that's gonna be it for this time. So thank you very much for joining me here and chatting with me and stuff. So have a nice day or evening or whatever it is over there.